Bismillahirrahmanirrahim. So let's look at another example of Fourier transform. In this example, we're going to look at how to compute a Fourier transform of a cos function. All right. So cos 2 pi f naught t, very important function that we normally use in signaling systems and communication systems. Okay. So we're going to start off with for basic definition of our Fourier transform. Fourier transform. If I want to find out a Fourier transform of any function, I will take that function, I will multiply it by e to the negative j 2 pi ft dt and limit as t goes from negative infinity to positive infinity. So we're going to do exactly the same thing. Here we're going to compute a Fourier transform of cos 2 pi f naught t. Alright, so the Fourier transform of this is going to be t as it goes from negative infinity to positive infinity. In place of x of t, we're going to put our cos function, cos 2 pi f naught t, and we have this kernel, which is a Fourier transform kernel, which is e to the negative j 2 pi ft dt. All right, so there's multiple way you can do it. I personally like the way I can replace cos using Euler's identity. So if I have 2 pi f naught t using Euler's identity, I can replace this with e to the negative j 2 pi f naught t plus e to the negative j 2 pi f naught t divided by 2. All right, so this is an Euler's identity. I'm going to use that in place of cos. So this would become t as it goes from negative infinity to positive infinity, and in place of this, so this is going to be e to the j 2 pi f naught t plus e to the negative j 2 pi f 2 pi f naught t divided by 2, whole thing multiplied by e to the negative j 2 pi f t dt. All right, so I'm just going to write it in terms of two different integrals. So this is going to be 1/2. All right, t as it goes from negative infinity to positive infinity. So this is just going to be a multiple of this. So this is going to be e to the negative j 2 pi f of t multiplied by e to the j. This is being distributed. All right, this is just being distributed. So this is going to be e to the j. Okay, so I'm multiplying this by this and this by this. So this is going to be e to the negative j 2 pi f of t multiplied by e to the j 2 pi f naught t plus e to the negative j 2 pi f naught t dt. I can individually write them like t negative infinity to positive infinity. So this, so when we have the bases same, I can add up the power. So the first one would become e to the negative j 2 pi f minus f naught t, all right, dt. The second one would become half t negative infinity all the way up to positive infinity, e to the j 2 pi f plus f naught t dt. I hope you all see this, because when I multiply this by this, I'll take that negative out. What happens when you have the bases same, power add up, but there's a negative sign? Same thing when I distribute this, I'll end up with this. So you can just split it out. I just split it out. I split that integral into 2. All right. Now the next thing is this. Imagine for a second right now, this t is being replaced from this t, and this is being replaced. And imagine something else. Just for the sake of simplicity, just to make us understand, let's just put 1 in front of it. All right. Let's put 1 in front of it, and let's change this t. Let's just imagine just t. So let t changes to f. So let this t changes to f. What will happen? Now basically what we're looking at, when I change this t to f, this is actually becoming a definition of an inverse Fourier transform. And this thing has 1 in front of it. What is the inverse Fourier transform of 1? All right. So if you recall from a delta function, so Fourier transform of your delta function, it is actually 1. But what is an inverse of 1? Fourier transform of 1. When I take an inverse Fourier transform, is actually becoming delta of t, isn't it? So I am actually making that replacement where I'm taking t is changing to f. This dt is becoming df. So I'm looking at an inverse Fourier transform definition. So this whole thing would become 1/2. Because of that 1, it's delta. And you can think of this 1 as being this. In front of variable, what is the number in front of a variable? It's just 1. That's why we have this 1. So this is f minus f naught plus 1/2 delta f plus f naught. This is the Fourier transform of my cos function. Right? This is a Fourier transform of my cos function. This is a very, very important function that we like to use in modulation and things like that. So how does this function look like? How does this function look like? So let's look at it in terms of time, and let's look at it in terms of frequency. So let's look at the figure of this. So in terms of time and frequency, this is how the graph should look like. Cos in time domain looks something like this. So it starts off, goes like this, like this. This is your cos function. All right. This is your cos function. In frequency domain, what that is, what is a delta function? Delta function is a function that is nothing but just like a straight spike, isn't it? It's just straight spike at t as t goes from -0 to +0, or basically it exists only at 0. It's a very thin line that exists when t is equals to 0. So think of it this as being this. So let's say this is your frequency spectrum. So this is time. This is frequency. So what this is saying, what this definition of cos, Fourier transform of cos is saying is this. In my frequency spectrum, my frequency is being shifted at some value f naught, and in negative, it is being shifted to some value at negative side, negative f naught. That's what it's saying. So my signal, and it's in which form? How does the behavior of that signal looks like? It's actually nothing but a delta function. It's like a straight spike that has an area under the curve of 1/2. Right? This is what this definition is saying. So every time you see in a book where for a cos function, or when you're doing modulation, when you see a thin line, this is actually to represent this delta function. And f minus f naught and f plus f naught is actually basically telling me the shift in frequency. So when you even look at it in a spectrum analyzer, you don't get to see this negative part. I will actually do a tutorial on this. You will never get to see this negative part because these spectrum analyzers don't give you. They only give you the positive frequency. There is no such thing as negative frequency. But negative frequency is coming through use of that Euler's identity, which we just applied here. That's why mathematically is coming in, but we cannot actually visualize negative frequency. There is no such thing as negative frequency, but it actually exists only mathematically. So it's a very important function. We use it a lot in communication system. If you have any questions, please don't forget to subscribe to my channel. And if you have any questions, leave it in the comment section.